Hi, welcome back. We're still in the Oscillations chapter, and now we're doing example problems from the end of the chapter. So, in this first one, to start off, we have a pendulum, and it consists of a massless rigid rod with a mass attached to one end, or attached on one end. The other end is pivoted on a frictionless pivot, so that the rod can rotate in a complete circle. The pendulum is inverted with the mass directly above the pivot point, then released. Released means from rest. The speed of the mass as it passes through the lowest point is 5 meters per second. Then they ask, if the pendulum later undergoes small amplitude oscillations at the bottom of the arc, what would F be? What would the frequency be? So let's draw what's going on here. So you have a mass attached to the end of a massless rod. So we have a rod here that is massless. And the reason they want it to be a rigid rod, because if this is a string, you can't hold the string like this and the mass above it, because it will just fall down. So it's pivoted right here. And let's say this rod here is length L. The mass is released from rest. And then what it does, it will swing. When it gets to the bottom here, they are saying that the speed, let's say it went this way. When it's at the bottom, the speed is V equals to then released. When the mass is directly below the lowest point is 5 meters per second. So 5 meters per second. So at the top here, the speed is equal to 0. And so let us find, we need to find the length of the rod. So what they're asking first, this is the first part. The second part, they say, let's say now we have the rod here, and we tilt it a little bit, so the mass was here. We tilt it a little bit, and then it will swing back and forth in simple harmonic motion. That is just, that's just the pendulum of mass m at the end, and it just swings back and forth. So if I know the length of the pendulum, if you remember that omega is the square root of g over L, and it's equal to 2 pi times the frequency. So the frequency itself, they want to know the frequency, would be omega divided by 2 pi. So the frequency would be 1 over 2 pi g over L square root. G over L square root. Right? Since I used capital L here, I'm going to use the same symbol, capital L. So if I know L, I'm going to know the frequency. So how would we find the length of this? Well, we know the speed here. We can use conservation of energy, because not because we're in the chapter of oscillations, it means we forget about the rest of the chapters. No, it's all related to each other, and it all can be traced back to Newton's laws. So energy is conserved. There are no non-conservative forces doing work. There is no friction or anything. So it goes down. Let's take this to be the 0. So when it's above here, there is gravitational potential energy, and it's equal to the mass times gravity times the height, which is 2L. So I'll just say this point here has initial energy. The initial energy there is no kinetic, it's all potential, and it's equal to the mass times gravity times the height, which is 2L. At the bottom here, the energy at the bottom is all kinetic. There is no potential. I'm taking the potential energy to be 0 here. That's my reference point. So it's 1/2 mv squared. 1/2 v squared. Bottom. And since there are no non-conservative forces, then the mechanical energy at the beginning and the end, they will be conserved. So we're going to say, all right, we got the energy at the beginning should equal to the mechanical energy at the end, and 2mgl will equal to 1/2 mv squared. The mass cancels, and therefore we have L will equal to v squared divided by 4L. Let's see. we divide by 2L, this becomes a 4, and the L is on the bottom. I think we have it right, yeah. Then we have the frequency, so we go here, plug it in. So we have the frequency equal to 1 over 2 pi times the square root of G over L. When we divide by L, we're divided by this. So when you divide, it's like multiplying by the reciprocal, so the V squared comes on the bottom, and then the 4L comes on top. 4L comes on top. Yeah. And I think we have it. Now we just, all we have to do is simply plug in the numbers. Let me get my calculator here. So it's just plugging in numbers. So 4 times G, that's 9.8, times, what did I do? I made a mistake here. I'm solving for L. So I divide by the 2G. So here it will be 4. The G will be here. G here. And so here, when you divide by it, 4G comes upstairs, so you get G squared. Yeah, now it's better. Let's see if it's, I think dimensionally it's correct, because G will have meters per second squared. When you square it, you get meters squared per second to the fourth, and here you get meters squared per second squared. When you square the V, yeah, I think it will come out to be 1 over seconds. So let me just calculate it. So I have 4 times 9.8 times 9.8, because it's squared, divided by V squared. V is 5 meters per second, so that's actually this even simplified. I don't even have to deal with the square root, because the square root of 4 is 2, and it divides this 2, so I just have 1 over pi, and then the square root of G squared is G divided by V. Yeah, that's way easier. Yeah, this is much easier. So I have 9.8 over 5 over pi, 3.14159. So I get 0.624. 0.624 hertz. Yeah, that wasn't too bad. Let me just double check the answer. We have, 0.62. Yeah, that's good. Okay, I hope this was fine. I don't think it was too difficult. Not the last, we're doing several. Let me put this one here. So let's look at this one here. They give you this graph. At t equal to 0, the position is 5, position versus time. At t equal to 0, the position is 5. Sometime later, the position is 10. The position is 10. And then it goes on, and it completes one cycle. It starts here, completes one cycle after 4 seconds. So if it completes one cycle after 4 seconds, it means the period is 4 seconds, right? Because the period is how long does it take to do one cycle, come back to the same position. So the same position in the same direction. So it's 4 seconds. So the period is 4 seconds. The first question they ask is, what is the phase shift? The phase shift, remember, is phi. So let me say here, I will just write it. The period is 4 seconds. Okay? We just read it off the graph. Therefore, omega, which is 2 pi over the period, so it's 2 pi over 4 seconds, 2 pi over 4, 2 pi over the period. And if you plug in 4 here, you get pi over 2. So omega is pi over 2. All right, good. Pi over 2, you can divide it by 2 and get numbers. So now we have, they say, what is the phase shift? So we know that the general solution for simple harmonic motion is x of t equals to some amplitude times the cosine of omega t plus this phase shift, right? Now at t equal to 0, well, first of all, let me write down also the amplitude. The amplitude is 5, right? The amplitude is 5. I'm sorry, not 5. The amplitude is the maximum displacement from equilibrium. The equilibrium is here. The amplitude is 10, sorry. The amplitude is 10. So at t equal to 0, x at 0 is half of the amplitude, is 5. The amplitude is 10, and then the cosine of 0 times omega is 0, and then plus phi. So cosine of phi. So I get phi here will equal to what? The cosine of phi is 1/2, so phi will be pi over 3. In fact, it is either plus pi over 3 or negative pi over 3, because remember the cosine of positive pi over 3, which is 60 degrees, cosine of 60 degrees is 1/2, and the cosine of negative 60 degrees is also 1/2. So how are we going to decide whether to take the plus or minus? Well, we can decide that by looking at the velocity itself, whether it is positive or negative. So now, is the velocity positive or negative? The answer is the velocity will be positive. Why? Well, because look, x started at t equal to 0, x is 5, and then it's increasing, so it's moving in the right direction, it's moving in the positive direction, that's why x is increasing. So the velocity is positive. So let me write down the equation for velocity. The velocity, so that we can decide on this. The velocity itself is the derivative of the position, so it's negative a omega sine of omega times t plus phi. Let me see what the velocity is at time t equal to 0. You got the velocity at t equal to 0 will be negative a times omega times the sine of phi, like so. Now, a is a positive always. It's the amplitude is always a positive quantity. It's a magnitude. Omega is always positive. Now, I want the velocity to be positive. I have a negative sign here, so I have to make this negative. Now, the sine of negative pi over 3 will be negative radical 3 over 2. It's a negative number. So negative times negative will be positive. Therefore, it means that, and I want, so that it needs to be larger than 0. That means phi will be a negative number. That means phi will be negative pi over 3. I hope you see why that's the case. So let's look at it from far away. What I used the initial position I plugged in t equal to 0, and I concluded that phi has to be either plus or minus pi. So I have to decide whether it's positive or negative. The velocity will tell me whether it's positive or negative. Since the velocity is positive, how do I know that? Is because x is increasing. It went from 5 to positive 10, and so it is increasing. So the velocity must be in the positive direction. Okay. So now I hope everything is clear. We can write down our position now fully. So x as a function of time will equal to a, the amplitude, that's 10, times the cosine of omega t. Omega is pi over 2. So pi over 2 times the time. The phi here, the phase shift, is plus negative pi over 3, so minus pi over 3. And that's the position, the full description of the position. The velocity as a function of time will look like so. It's negative a omega, so minus, the amplitude is 10. 10 times omega, omega is, we said pi over 2. So 10 times pi over 2, that's 5 pi, so negative 5 pi times the, not cosine, sine of pi over 2 times t minus pi over 3, like so. You might be anxious to just plug it in. You could just simply plug it in, but I would just say, hold on, don't replace the numbers with, like pi is an exact number, but don't replace it by 3.14159, etc. Don't do that yet. Just hold on. And the acceleration is the derivative of this. So the acceleration will equal to, when you take derivative of sine, you get the cosine pi over 2 t minus pi over 3. And when you take the derivative of the inside, you get the chain rule. Derivative of pi over 3 is 0. Derivative of pi over 2t is just pi over 2. The pi over 2 comes out, and it gives you a 5 pi squared divided by 2. That's the acceleration. Now we have everything. We answered this. What's the phase shift? We have answered this question. Now it says, what is the velocity at t equal to 0? Well, plug in t equal to 0. and see what you get. You get the velocity at t equal to 0 will give us negative 5 pi, negative 5 pi, and then the sine of, this is negative, pi over, I'm sorry, not negative, pi over 2 times t at t equal to 0, that's a 0, so the sine of negative pi over 3, and the sine of negative pi over 3, the sine of 60 degrees will be radical 3 over 2, but it's negative, so it will be negative square root of 3 over 2, and you get a positive 5 over 2 pi times radical 3. You can plug it into the calculator. I might do it later. That's the velocity at t equal to 0. Maybe I should do it. So that's just for practice. You got the square root of 3. Let's see, 3 to the power 1/2 to get the square root of 3, and then multiplied by pi, and then multiplied by 5 over 2. I get 13.6, about 13.6. So that's about 13.6 meters per second. That's the velocity at t equal to 0. So that's good. And then what is the maximum velocity? Remember, maximum velocity, this function here, sine oscillates between plus and minus 1, so the maximum velocity is just this number, 5 pi is what's in front. That's the maximum speed and maximum velocity. The velocity will be, the maximum velocity will have a magnitude of 5 pi. Yeah, so V max is 5 pi. And 5 pi is about 15 or so, or 16. About 15.7 meters per second. Let me just double check all the numbers to make sure I have not made any mistakes. We are in problem number 7, and I get 13.6, 15.7, and I'm actually yeah, that looks okay. That looks good to me. And what is the other question here? It says, what is Vmax? Yeah, we answered everything. For some reason, I thought there were more questions than this. Or maybe I'm thinking of another problem. So that is good. All right? So just be patient. Write down this function. You will get usually two possibilities for phi, because the cosine is an even function. So you get either plus or minus. And then you have to, whether to decide the plus or the minus, you have to look at V. And here I knew that V is positive, because here is the mass on the spring. The spring at t equal to 0 was at 5, and then, but a little bit later it was at 10, so it's moving in this direction, so the velocity I knew was positive. Okay. Let's look at the next question. It says here a uniform steel bar swings from a pivot at one end with a period of 1.2 seconds, and the question is, how long is the bar? So this is it's a uniform bar, so the mass is not at the end. It's not just it's uniformly distributed. So if you remember, here is how it looked like. Just try to, so here is the bar. It's pinned here, and it swings back and forth. Right? It swings back and forth. So this is the center of mass. So there is mg this way. So gravity would have a component in this direction and a component in this direction. The component in this direction cancels the component from the pivot point that's this way, but this is the component that causes the torque, and it is, if this whole length here is L, this is L over 2, so the torque, we know that the torque is equal to I times alpha, Um, and the torque is the force itself, or the component of the force that's perpendicular to the direction of motion, that's mg sine theta. And we said this is a clockwise torque when theta is positive, so it's negative. So this is the force times the distance from the pivot point to where the force is applied, that's L over 2. L over 2. And we get this. I think we have everything. And then the moment of inertia for a rod about a point through the edge, if you remember, the moment of inertia for a rod about some pivot will equal to the moment of inertia about the center of mass plus the md squared, the mass times the distance squared. This is the parallel axis theorem. The moment of inertia for a rod about the center of mass is 1/12 times the mass times the length of the rod squared. And then plus the mass times the distance from the center of mass to the pivot point is L over 2. So the mass times here L over 2, and we square it. So we get 1/12 ml squared plus 1/4 ml squared. And when you add a 12th plus a fourth, you get what? 3 over 12. So you get 4 over 12, which is 1/3. Yeah, that sounds correct. 1/3 ml squared. I didn't want to rely on just memory, but I was pretty sure it was 1/3. This is how you derive it. It's extra practice. Okay, so you get here the moment of inertia is, what did we say, 1/3 ml squared, and alpha is the second derivative with respect to theta, d squared theta dt squared. And what we have done is, so let's cancel the mass and this L. And so you get negative multiplied by 3. So you have 3 over 2 from here. And then G divided by L. So I have G over L. And hopefully I don't make any mistake. Sine of theta is equal to the second derivative of theta with respect to t. We used the small angular approximation for theta, so we said sine theta is approximately theta. So we said, all right, the second derivative of theta with respect to time will equal to negative 3 over 2 g over L and then theta, and we identified this thing here as omega squared, and therefore omega will equal to 3 over 2 g over L square root. And so the period, which is 2 pi over omega is 2 pi over the period will be 2 pi over omega, would be 2 pi 2L over 3g. And I think they want just, that's fine. All right, they gave us the period and they want L. I forget even the question. That's fine. We will, now we have the period, we have this. So let's divide both sides by 2 pi. So I get the period over 2 pi. And we square it. That gives you 2L over 3g. So L will equal to 3 over 2, or 3g over 2, times t over 2 pi, the whole thing squared. All right, let's plug in some numbers here. Where's my calculator here? I get what? The period is 1.2. Divide that by 2 pi. Square it. Multiply it by 3 over 2g. 3 over 2 times g, 9.8. I get the length of the bar is 0.536. Hopefully that is the answer. This is number 31. I got 0.536. Yes, so that's correct. So you get 0.536 meters, approximately or equals to 53.6 centimeters. I think there are two significant figures. Don't worry about that. So that's about 54 centimeters. So the book just writes it as 54 centimeters. All right. So that's that. I will do one more problem, and then I want to do a more challenging problem. All right. Let's read this one. Number 40. A block attached to a spring with force constant K equal to 2.5 newtons per meter. It oscillates horizontally on a frictionless table, so no friction. Its velocity is 20 centimeters per second when x is equal to -5 centimeters. What is the amplitude of oscillations? What is the maximum acceleration? What is, when the acceleration is equal to a maximum, what is x? And then when x is equal to 3 centimeters, what is v? I feel like this is probably a conservation of energy. Let's take that approach. And I usually take the conservation of energy approach until I run into trouble, and then I might use something else. So solution. First I have the mass, and I have K. Why not calculate omega? K over M. Again, I need my calculator. K is 2.5, and the mass is 100 grams, so that's 0.1. So 2.5 over 0.1. No calculator, actually, because this is just 25. Square root of 25 is 5. So 5 radians per second. That's omega. They give us the velocity when x is equal to 5 centimeters. They say, what is the amplitude of small oscillations? Well, we can simply find out what the use conservation of energy. We would say by conservation of energy, we have the total mechanical energy is 1/2 Ka squared, and that's equal to that's the total energy at all times. And at this particular time, we can set it as 1/2 mv squared plus 1/2 kx squared. Multiply everything by 2, and then divide by k. So you get the energy would equal to multiply by 2, so the 1/2 simply goes away. Divide by k, you get you get just on this left side you get a squared would equal to m over k and v squared plus x squared. So to get the amplitude, just take the square root of this. So let's do that. The mass over k, the mass is 0.1 and k is 2.5, so 0.1 over 2.5. The speed is 2.5 centimeters per second, so that's 0.2 meters per second. So times 0.2, but don't forget to square it. And then plus x squared. X is -5, but 5 centimeters, that's 0.05 meters, but don't forget to square it also. Plus 0.05 to the power 2. The negative goes away anyways. And then don't forget to square root now everything. And we get the amplitude. The amplitude would be 0.064 meters, which is 6.4 centimeters, which is good. The amplitude better be at least equal to that. It would be larger because the speed wasn't 0. So 6.4 centimeters, that's the amplitude. Then it says, what is the maximum acceleration? Remember, the acceleration is given by this. The acceleration is a function of time, would be -a omega squared, the cosine of omega t plus phi, right? And so this part here will be the maximum acceleration. Because when you plot this cosine function, it will look like this. And this is the acceleration, and this is time. And the acceleration will fluctuate between these two numbers. In magnitude, it's this number here. And so that's a omega squared. So the maximum acceleration will equal to a times omega squared. And we have the a, and we have the omega. So the a is this times the omega squared. Omega is 5, so 0.064 times 5 squared. So times 25. So I get 1.6, about 1.6. meters per second squared. So that's this part. They say when the acceleration is equal to the maximum acceleration, what's x? What is the position? Well, when it's the maximum acceleration, when do you get maximum acceleration? It means you have the maximum force. When do you have the maximum force? Well, the maximum force is when you have the maximum stretch. Because remember, the force is the force from the spring. So when x is equal to either plus the amplitude or negative the amplitude. Now, here is the spring, and here is the mass. And let's say this is the maximum, this is the zero, and it oscillates between a and minus a. So this is the x-axis. When it's here, the acceleration is negative. It's to this side, but it's 1.6. And when it's here, it's to this side, and it's positive 1.6. And so if we want the maximum acceleration, which is positive 1.6, it's in this direction, and so x will be at negative a. So when the acceleration is the maximum, x will equal to negative a, which is negative 6.4 centimeters, or just negative the amplitude, negative 0.064. And then it says when x is 3 centimeters, what is v? When x is 3 centimeters, what's v? Well, we know again the total energy, which is 1/2 ka squared, is equal to 1/2 kx squared plus 1/2 mv squared. So this goes away, and we want to solve for v. So let's move the x to the other side. So we have mv squared will be k, and then a squared minus x squared. Divide both sides by the mass, so this goes away, and then take the square root of both sides to get the v. All right? And so I want the v when x is equal to 3 centimeters. Just the magnitude, what's the speed? So we plug in the numbers. So we have the k, and we have the m, and we have the a, and we have the x. So I have k is 2.5. The mass is 100 grams, that's 0.1. Multiply that by the 0.064, 0.064. Don't forget the square. And then subtract from it the x, which is 3 centimeters, or 0.03 to the power 2. And so that's that. Take the square root to get the v. I get 0.28. So I get, when x is 3 centimeters, v is 0.283 meters per second, which is 28.3 centimeters per second, since they're working with centimeters in this problem. It's safer to just go to meters, and then you can always change back to the centimeters.